I'm going to speak about the generative-discriminative basis learning for medical imaging. The presentation will be in the two parts. Today I will have a brief description of the paper, and for the next session I will go to the detail of the techniques for projection and sparsity finding in this paper. Let me first introduce what's the paper. The paper is for it's a technique for extracting and selecting the feature from 3D data of not 3D data, for the medical data, and the purpose of the paper is they want to, for example, extract the features that these features has a discriminative property. It means, for example, if you have this feature, you can find the difference between the tissues, and also these features must represent some anatomical information of the body. For example, if you have the data of for example MRI, and you have a 3D data, and you, for example, can apply a different classification technique to separate the different tissue. But if you have a lot of data, you want to, for example, extract a vector feature, that this feature vector is not, for example, too long, and this for example, not too long vector explains some property of the body. For example, if you have a, as I said, if you have a MRI of the, for example, body, for example, if you can find a feature that this feature was short, and explain, for example, this one is the bone, it's a good feature because also it's a short, it's not too long. And also, if you find this feature anywhere in the body, you can say, for example, with a good belief that this part of the body is bone. It's example of this. And for finding the feature, there is a lot of techniques for example, feature extraction and feature selection. For example, if we select, we have some sample of data, and we want to, for example, extract some feature. We can do two types of the dimension reduction or feature selection from this type of data. First type is the generative, something like PCA. You can find the most the name of PCA is principal component analysis. It means you want to find the axis in the data that most of the data is around that axis. But there is another type of the dimension reduction. It's for example, the most common technique is the FDA. Feature discriminative analysis. The difference between PCA and FDA is in the PCA you want to find the best dimension into your data that can describe your data, but in the feature discriminative analysis or FDA, you want to, for example, find the bases that with these bases you have best discriminative line or hyperplane that, for example, you can distinguish the two types of the data with two different labels. And also, if, for example, this paper wants, it is trying to find some type of the mixture of the, for example, generative and discriminative feature from the data, which this type of the features can represent the original data well. Also, it must have some anatomical information of the body. For example, the paper is speaking about the image of the brain, and they want to, for example, extract a feature of the brain, but they know, for example, some special area in the brain. For example, some part in the bottom of the brain, and they want to, for example, parameterize the some mixture of the generative and discriminative features to extract the best features which has some information of the body. The two main, as I said, the two main purpose of this paper, first is the basis vector should be anatomically meaningful, and the second one is the basis must be discriminative. And for doing these two properties on the paper, they use the simple, not simple, but it's a mixture of the it's a mix. It's somehow modeling the problem with map estimation. Let me explain a little more about for example, the difference between techniques. In the noun techniques, for example, extract the feature, we have, for example, some techniques that we have a big matrix of the sample data. For example, if we have a sample data, X is for example, the number of samples is n and the dimension is d. And there is some techniques, for example, like maybe SVD, maybe k-means, as thing in the one of our meetings said, maybe it's non-negative matrix factorization. They are the techniques that you can, for example, factorize the matrix and find the basis that can represent the original data very well. If I want to, for example, list some of them, it's, for example, SVD, k-means, non-negative matrix factorization. There is some measurement to, for example, convergence of these methods. For example, in SVD, we try to find the Fabius norm of between D and BC. Here we want to, for example, model the X as a two matrix B, which are our bases, multiple a matrix C, and for example, we want to have a X, it's similar, it has a less error. We can, for example, reconstruct the original data with a little error by a basis function B and a matrix C. And for example, we have a different measurement for the error here. For example, in SVD, term that's this is the values norm between x and b multiple c, and there is a lot of there's also some constraint over b, and b multiple b transpose must be identical, and also c multiple c transpose must be the I matrix. This is, for example, for the SVD, and for example in k-means the part for measuring differences between the B and C is the same, but we don't have any constant on the bases, and we have only C multiple C transpose must be identical. And for example, for the NMF, we have the KL function between X and BC, and the BIJ and CIJ must be positive, not negative. Okay. Here for formulate the problem with the map estimation, we have some assumption that, for example, the B is the matrix. For example, BI, all of these elements are the column matrix to BK, and the dimension of each of, for example, BI. The dimension of B is equal to the dimension of the X. For example, I can write it down as RD. And same for the C and C1 to Cn. The n is the number of the samples, and each of CI's belong to RK, and we have a matrix W that vector W that is RK. Here in here, as I said, we have the X equal to BC, and for represent each vector in by this basis function, for example, mu vector y is equal to the X transpose multiple B, and a weight function that this weight controls the value of bases based on the original data to create a y. Y is the label of the matrix. For example, we have X, I, and we know what's the label of that. The label of that is, for example, yi, and maybe this is a CI and BI, which are related to which and for example the multiplication of these two create a xi, and the dimension of these three is k, and this one each element has d, and the w it's a vector by the number of this the number of Ci, Xi and Bi is equal to the number of the samples, it's n, and the number of Bi it's equal to k, the dimension of the Ci, because it's trying to select some of the features to create original data. And they estimate, they formulate the map estimation here by arc marks of log probability of B, C, and W when we have the samples X and the labels, which and we can expand this one. It's equal to arc marks of log P, B, C, X given B and C over B, C, and W plus log P of probability label given X, B, and W, and the log of probability B plus yes. And this term is equal to, for example, the K and B between X and BC, and they call this form as term, and this term is the discriminative term. And these three terms together, it's some constraint. If yeah, and instead of finding the maximum here, they try to use the minimum of the minus of this term, and when we find the minimum of this term,
condition probability, can you induct
condition probability here.
From the first step, because so many.
Okay, there is some relation. For example, if we have, for example, P X, Y, Z is equal to P X given Y Z plus P Y given Z plus P multiple PZ. If we have some relation between these three terms, something like X okay, we can split this probability to these three if we have some relation between these three variables, something like this. Okay.
I want to interrupt because actually that one is completely general what you written down. It doesn't matter what kind of graphical model, like the variables, any three variables can be written like that.
Yeah, but for example, if we have X, Y, Z, and it was something like this, then for example, instead of using probability of X given XY, we can write it down as probability X given Y. I think it's true. I said this shape because I want to, for example, show the relation between all of them. And here, based on this diagram, we have probability of BCW given X, Y, and it's probability of x given b, c, w, y given probability of try the reverse one. We have the probability of PB, PC, PW, and PY, X, BW, and X, BC. And in the posterior probability, we want to, for example, if we have a p x given y, it's equal to p y given x, p x over p y. For finding this one, we have the pxy given bcw multiple pbcw. We assume these three are independent, and we can, for example, use the pb multiple pc multiple pw. Okay, and for this term, we can use px given y bcw multiple py given bcw. And this one is this term, because there is no relation between.
You flip actually.
It's flip.
Yeah, I think you flip. You want to have like px given bcw and py given xbcw instead. No, that equation there. You want to the first one you don't want to have condition with y. The second one, you don't want to add the condition with x.
This one you mean?
This add condition with x. Py given x bcw. The other one is p. Oh, that's the line behind
this one.
Yes, below that one. Yes, yes. Without the condition on y.
Okay.
But the other one with condition with
yeah.
x. Yes.
Yeah.
Yes.
Yeah.
Oh, this condition is x. The second time of condition with x. Yes.
And here we have this term BC and W is not, there is no relation between W and XI, and because of this, this probability of X given BC W is equal to probability of X, B and C, and for this term, there is no relation between y and c, and because of this, this is equal to p y given x, b, and w. first time generative term, it was the, I said instead of using the maximum here, we can use the minimum on the minus term, and it will be equal to the R mean of BCW, and we call it DX and BC, and the minus log P, log probability of X given B and C, it's equal to lambda 1 multiple the multiple of the divergence between the data X and BC, and this one is equal to, for this paper it's lambda 1 and norm 2 of BC, and this function is a convex function, and they can, for example, use some solver to solve this term. For the discriminative function, they define a function, they classify a function HW of X, which is the inner product of the W and B transpose X. And for this term, they use they call it this one D of X, BC, and this one is L of Y.
What was D?
D is a divergence measurement. It's the measurement to keep the decomposition part as similar as possible to the original data. Because in the decomposition part we have the X equal to BC, and this term will be controlled, the decomposition term, the bases multiple the C are similar as possible to the original data, and this term will be controlled this one. And for L term, it's for the discriminative. It means we find some bases that this bases has better separation between data. For example, let me explain this. For example, if we have 2D data and we have for example dot here, and for example, if we want to have a best, we want to select the best dimension to describe this set of data, maybe we can, for example, use this one as a this one is x1, x2, and this can be x1 prime, and for example this one can be x2 prime in the, for example, PCA, to find the best dimension to describe the data. But if we have a label and we want to find some feature that can separate the data, maybe instead of using the, for example, this one, xprint1, is the best dimension to describe the data, because all of the data here are collected here, and all of the data here, if you map they are here, and there's a good gap between two sets of the data. But if you do something like this, you will miss some information of the data, because you don't have any information about, for example, what's the variance of the data in this direction. The first term, try to keep as much as possible information in the data, and the second term, try to push for example, the dimension in somewhere that it has a good discriminative property, and also for example, for the solving this technique, they use some sparsity constraint to select the dimension. This sparsity constraint try to push the bases to some informative bases. For example, as I said before, for example, to find some special part of the brain. For example, this one is the shape of the brain, and if you do, for example, the PCA, you will have some this one is 2D, but if assume this one is up and this one is bottom in the 3D shape. Okay, we have some 3D shape for all of some 3D bases for this shape that, for example, can explain. For example, we have some set of this type of the features, some set of bases that can reconstruct the original data, but as you can see here, there is no relation between, for example, the bases and the whole data. But by applying this constraint, for example, the first one, try to, for example, keep all of these bases. If you do the multiplication over all of them, the original data will be very similar to this one. And for discriminative, they try, for example, if this is the shape of the brain, for example, they try to find some part of that as a feature and the rest equal to 0. And if this part was the match to the anatomical information of the body, it's a good sign to, for example, continuing. And for creating this one, they applied some constraint extra to the L part. This constraint makes the bases collected, or it's dense in some area, because we assume the bases must be sparse. And this sparsity, there is also two types of sparsity: sparsity on the group and sparsity on the box. I will explain it more in the next meeting. But here, when you apply the sparsity, you mean you want to, for example, extract the bases which are collected in some area, and it's increase the chance to find some information of the some basis of this data that is matched to the anatomical information of the body. And yeah, and the way of solving this posterior probability, create bases which can satisfy, as I said, these three property for the paper. I don't know, you want to continue, or for the next session I want to, for example, again review these 3 parts, and I will go to the detail of how to solve each of them. The first one is not too hard. There's a lot of solver for solving this one, but for the second term, for the solving this one, there is some assumption, and they put some extra constraint to satisfy these properties.
What's the title of your paper proposal?
What's the title? It's Generative-discriminative basis learning for medical imaging. It's for the brain modeling, and there's a lot of experiments on the medical images, and also there is some experiments on the, for example, the text data, and text data, and I think one of them is the 2D image. No, it's some UPS data, USPS data. It's some information data to retrieval part data.